we did this, we did this thing with this I of x, where you took the ddx of the delta. And I'm thinking that's what I need to do in the homework, but I don't know why you did this, and I think it has something to do with this, but I'm kind of confused.
This became this probably.
Because you're evaluating the limiting case, I guess, or?
I don't remember. Because this is probably not the same as this. This is another integral, I think.
Okay, I see.
This is one, this is second.
I see. Okay.
Like, I think this is a result, and probably I asked you
To evaluate it in a
evaluate
limiting
this.
case. I
Yeah,
see.
I think that's what it is.
Okay.
And yeah, that's what it evaluates to actually. Yeah. This is an answer for it.
Mm-hmm. Yeah. Yeah, on the homework, I was missing the
Day.
yeah.
Yeah.
So I don't know, maybe I did the binomial wrong, but I don't know.
Yeah, let's like I plan to go over that a little. So let's hope.
But you said those are two different.
Yeah, at least in your notes, those are two different results. Does that give a little hint?
Yeah.
Let's say homework 3. Let's make it due 11. Thursday. And but if it's okay, I'll still have homework 4 due the usual next Tuesday. If necessary, we can postpone that, but I think once you get some examples, very similar problems. Okay. So we went over some examples on functional derivative. So let's get back to the main problem. We wanted to minimize functional, correct? So let's do the very broadly, since there is a homework problem involved, this shortest path on a plane. So let's do that. I'll come back and actually do more problems on that. Like we can do what is the shortest path on a cylinder. Like if you're on the surface of a cylinder, what's the equation of the curve that's the shortest in that? What's the shortest path on a sphere? Like that's what is the shortest path on a sphere, by the way? Are you aware of the result?
From not to the path, like from.
Yeah, if you're confined to be moving on the surface of a sphere, I think the best example is if you take a flight from, let us say you are to go from New York City to France, right? What's the path that you would take? Have you noticed? By any chance, have you traveled? Have you got a chance to travel? Like if you travel, so one would think. Okay, yeah. So there's a map here, right? You typically look at a two-dimensional version of the three-dimensional map. So let's see. I'm going to make boxes. So that's US. Okay. So just again. So that's South America. That's triangle, I guess. So that is the Europe somewhere here, I guess. Correct. So like this, and probably Africa is a big triangle. And reasonable. Okay. Lovely. So now suppose you are to go from, so Paris is somewhere here, I guess, and then New York City is somewhere here. What's the shortest path connecting? But you have to imagine that this is on the surface of a sphere. It is tempting to think, since we are mostly looking at a flat map, it is tempting to think of this to be the straight path. But most of the time, this path actually is like this. It will actually go all the way to London and then go to Greenland, and then actually something like this. If you go all the way to Greenland, Greenland is way up there, right? And one would think that why is the flight doing that? Is actually, if you put it on a surface of a sphere, it is the shortest path. It will always take the shortest path. It is not. I don't think it has anything to do with being more on water or more on, like often that's another question that comes up. If you have a choice, would an aeroplane prefer to go on water or on land? I don't think those are, again, these are my bias. I don't think they are very important parameters, except the gas itself. Gas is expensive, so we try to save on that. And this is the shortest path. So then the question is, how do you find the shortest path on the surface of a sphere if you're confined to be traveling on the surface of a sphere? It turns out the way to do it is that imagine a full circle. It is called, what is it called? It's a great circle. Right? Great circle is between any 2 points. So if you have a sphere, that's your sphere. Right? Think of a few points like this. Connect those 2 points using a circle. Right? But there are many circles that goes through 2 points on a sphere. But there is only one circle which has its center on the center of the sphere itself. So that's called a great circle. Like equator is a great circle, right? Whose center of the circle coincides with the center of the sphere, then that's called a great circle. Is that reasonable? So between any 2 points on the surface of a sphere, you can always find there is a unique circle that goes through, or there is a unique great circle, and the line that the curve that connects those, the shorter of the two, there are 2 of them, right? Other way also. That's the shortest path on a sphere. Right? Is that you can imagine that? But then you should say, why is that result true? Right? You should be able to find that out, and we'll try to do that. I'll do that in the class, but So basically, one should be able to, the examples you can try is on a plane, what is the shortest path? And these are called geodesics, by the way. Geodesics is the curve connecting 2 points on a surface is called a geodesic. It doesn't have to be a geodesic in any space is a geodesic. In a plane, it is a straight line. On the surface of a cylinder, you can think of a geodesic. Cylinder is pretty easy because you can cut the cylinder and it becomes a plane. So basically, a line that is folded onto a cylinder is basically the same. So a cylinder and a plane are simple. And then you have sphere. I just talked about it, but we will do that in the class. You can think of it on a cone. A cone is interesting because if you're in a speedway, like if you're driving a car, a sports car in a race, in a racing event, usually those roads are banked. So that's basically forms the surface of a cone. And you might be interested in the fact that on what path should, so for example, if the race car has this as your, as the, what is it, the lanes, and if the race car has to go from here to here, would you take this path or would you go like this? So there are various, and you might be interested in finding out, oh, how do you do that? And then you're interested trying to find out what is the shortest path on the surface of a cone. Right? So those are questions you can ask, and all these have similar approaches. So let's do the simplest case, which is also part of your homework, and let's do the geodesics on a plane. Right? So geodesic. I think it's geodesics because there are more than one, right? Given 2 points, there is a single geodesic, but in general, geodesics on a plane. And we're talking about two-dimensional plane. So there is 2 points, and out of many paths possible, so this is x1, y1, and x2, y2. And it's expected that the shortest path is the straight line. That's what we sort of intuitively know, that it's a shortest path is a straight line. But let's see that it is indeed a minimum of this point. If you have a small element there, so that's your ds there, so that's ds, you can form a triangle there, and ds square is equal to dx square plus dy square. So that's the distance along between any 2 points. Where do you get that equation from? We know that any distance between any 2 points, let's call it let's say delta 1, 2, right? That's the distance between 2 points, is equal to x2 minus x1 square plus y2 minus y1 square. Right? So if they are infinitely small, x2 minus x1 is really small, then you would say the line element on a path is given by ds square is equal to dx square plus dy square. So the path or the total distance for any path connecting 1 and 2 will be, let's say that's L. So you just integrate over ds, and you have to specify the path. So that's x1, y1 to x2, y2. And of course, this depends on a path, right? Going from 1 to 2. How do I specify that? So either I say this is the, so I have to specify the path, PADH, right? Or I can say, oh, this is, I'll get rid of the path and say this is a functional of y, where y is the path. So y is any possible function there. And in that case, I would say this is now an integral starting from x1 to x2. I don't have to say x1, y1 to x2, y2. Now I'm thinking of y as a function of x. So the moment I say x1 is given, then y of x1 is known. Right? So in that sense, I don't have two variables there. And ds, and let me say this is ds. So that's the same as x1 to x2. And ds is, I can take the square root out, right? So this is square root of dx squared plus dy squared. But it is nice to think of dx as a line element. Take that out, and we get x1 to x2 dx 1 plus dy by dx the whole square. It is good to imagine that y is a function of x. That's understood. I was trying to avoid writing that to avoid some clutter. So that's our functional. Right? And this is true for any function y. So so what we have here is that we have an x1, that is an x2, and that's your y of x. And given these 2 points, we have a general function y of x like that. And but we would like to know which one is which path, for which path is this length the minimum? The length of this path should be a minimum. Right? The construction of the problem is clear, I suppose. And let's say, so idea would be, so how do we find the minimum path? Our extremum condition is that now this is a functional. So strategy would be, so extremum, right? So extremum condition. So how do we find the extremum? If you have a function, you take, say that the derivative is 0. So this time the functional derivative will be 0. So dl as a functional of y with respect to y of x. Given any path, you make a variation in the length with respect to y. You make a small change and you require this to be 0. Slope. Think of slope if you're thinking of it as a one-dimensional thing. But here we are saying this is a functional in the sense that make an arbitrary change in the function and that should be equal to 0. And that requires us to investigate what is the derivative or what is the functional derivative of this L. So you can say that this is the condition for the extremum. And that again is L of y. Okay, is the question clear? Okay, so we want to find the functional derivative. For that, we need to find the change in L of y, right? Right away, it is, since we want to have with respect to x, right away here you can make this as x prime. It doesn't matter, that helps. And let's do, first of all, what is L of y plus delta y? Because delta L here is change, make a change in y and then subtract it out. Right? So that's equal to x1 to x2 dx prime 1 plus, wherever you see y, we have to make a change. So that's dy by dx prime plus d by dx prime of delta y of x. Notice this is also x prime. Notice that's also a function of x prime. So this can be done in 2 steps, d by dx of y plus delta y prime, and that's square. Is that clear, Christians? Okay. Since we are making a small change, I want the leading order contribution after I subtract, or I need the next to leading order, because the leading order will subtract out when I subtract the Ly. So I need the next to leading order. So we want the delta y contribution. This is square root. Expand this out. So that's equal to x1 to x2 x prime. Or let me do this in 2 steps. Y prime plus 2 times and d by dx prime plus, let me say, order delta square. That's basically, this term is nothing but d by dx prime delta y the whole square. But that's a delta square term. I just write that down as delta square term. Is that okay? Or there's nothing wrong in writing the complete expression, but I'm trying to emphasize that that's not really relevant. Okay. As of now, it is straightforward algebra, but now somewhere we have to start making approximations, or it seems like it is an approximation, but it's actually exact in the limit delta y tends to 0. So it's not really an approximation that we will be doing. It's not a neglecting, it is actually, it will not contribute in the limit delta y tends to 0. I will write one more step here, so that's equal to x1 to x2 dx prime 1 plus dy x prime over dx prime whole square. So I take that out, and what I get is 1 plus, so since I've taken this out, we get 2 times dy x prime over dx prime. I have d by dx prime delta y x prime divided by this whole thing, 1 plus and order delta square. This whole thing raised to 1 by 2. Doing this slowly, but pretty much we want to do binomial expansion. We want the leading order in delta y. Let's see. Questions here? Come on. Okay. So we would like to do delta L, the change in the functional, but L of y plus delta y minus of L of y. Like change in the functional because of the variation in delta y, and later we will divide that out by delta y2. Okay. When I subtract out, the first term actually cancels out, or before that actually, maybe I should do one more step, right? So I should say this is how y plus completeness. So remember 1 plus, so we have a square root there. So we have 1 plus some quantity. Should I write x? X could be confusing. 1 plus alpha, right? Of raised to half is equal to 1 plus 1 by 2. It is n actually. And it doesn't have to be an integer or any n. The series is n times n minus 1 over 2 factorial times alpha squared plus order alpha cube. Right? That's what we want, only leading order, or that means up to alpha. It's not really leading order, next to leading order, because the leading order will cancel out from L of y. I need the next to leading order. That's what derivative always gets contribution from the next to leading order. In that sense, L of y plus delta y then will be equal to x1 to x2 dx prime. The first term is simply 1 plus dy by dx prime whole square, that's 1, and now plus 1 by 2, and this whole thing, dy by dx prime, d by dx prime times delta y of x prime divided by 1 plus and you can say next term will contribute. Any questions there? When we subtract out, when we calculate the change in y, as a change in the functional, notice L of y is nothing but this first term. First term multiplied this was our original length for an arbitrary y. These two cancel out in this term, and what we have remaining is the change in the functional is x1 to x2 dx prime. Oh, I missed a 2, I guess, right? There's a factor of 2 here. So I missed the 2 there. 2 cancels out, and what we have is dy x prime over dx prime, d by dx prime delta y of x prime. Right? That's a function. This is a change in the function of y of x prime divided by, there is a square root here, which I have to multiply with this. So this is 1 over square root of dy with respect to x prime over dx prime squared, and that is the square root. So that's okay. But we are interested in, this is the change in the functional due to y, but the functional derivative will be the ratio of this to the change itself. Right? So this is delta L y. We are interested in divided by delta y of with respect to x, some function, arbitrary function y of x. But this whole thing is a quantity dependent on x prime. So wherever I can actually move this change y delta y, the ratio of delta y inside and outside of the integral. So I can move it in. So conveniently, I will do x1 to x2 dx prime and dy x prime divided by everything is x prime dependent, so it doesn't contribute. And I will take it all the way down to delta y of x prime and delta y of x. We have a limit also. When we take a functional derivative, it is understood that we are taking the limit. So we also have the limit that delta y is 0, which we often don't write. So it's good to. Is that clear? Notice most of this was algebra in the sense I was trying to get the leading order contribution from delta y. That was most of the algebra. And once I have found that leading contribution, then I bring in the ratio or the actual derivative, and this then is identified as a delta function, right? That's what we said, and that the meaning there is that the variation in y at x prime is independent of the variation in y at x, unless x and x prime is the same. If x and x prime are independent, that's 0. If x is equal to x prime, it should actually be equal to 1. But since it's an infinite set of contributions, we need a delta function because they all have to add up to 1. Right? So due to that, we have to have a delta function. In general, if we are having discrete quantities, then it just has to be 1. Right? So that's a delta function. So if that's a delta function, that's equal to, proceed, x1 to x2, x prime, and this is dy, x prime over, so that's a function here. It's d by dx prime of delta function. Okay. But let's recall. Let's try to recall. What is if I have an integral x1 to x2 dx prime of f of x, right? Some arbitrary function. And if I have a delta function x minus x prime, what is that equal to? If this was the case. Like that's not what we have. But if we had such an integral, what is that equal to? F of x, correct? And here the understanding is that x prime or x is in between x and 1, between 1 and 2, somewhere there is a value where it matches. Now, one more identity is x1 to x2, x prime, f of x prime, derivative of a delta function. What is that equal to? F of x times the delta. No, you will operate this on the left hand side. You integrate by parts, so it's a few steps. But as a result, this is what I want you guys to. This is always f of x prime derivative. Again, if x is within x1 and x2. Right? Yeah. There are boundary terms, but at this point, I'm just keeping this. There is usually a boundary term also, but let's just have this. Okay? Later, we'll come back and do. If you want how this comes about, this is equal to actually integrate by parts, correct? So this is x1 to x2 dx prime d by dx prime of f of x prime times, but that's obviously not equal to that because this acts on both, so you subtract that. Okay. Now, this integral now we know because this is a delta function, pure delta function, right? It's not a derivative. And this one contributes only at the boundary. This is f of x2 delta of x minus x2 minus of f of x1 times delta of x minus x1 minus of derivative of x with respect to x. Is that clear? Oh, this was not prime, right? This was only x because prime is integrated. Is that clear? But here we are saying that, oh, there is no variation at that boundary point, so these two don't contribute. It's just that. So when I wrote this, I assumed that these two don't contribute. But it is good to see that as a result itself. It's convenient to use that just right here, then you can write the next step that instead of doing that in 3 steps. Okay, clear? So at this stage, assuming that the boundary points, there are no variations at the boundary, then I can actually proceed and write this as because this is equal to, I just evaluate this at d by dx, right? D by dx of, oh, this was d by dx prime. Does that help? This was my function f of x. I have to take the derivative of that. Negative. Negative. Yes. Yes, yes, yes. Thank you. Maybe that was good. So if the exercise is just telling you to find the functional derivative, that's a functional derivative. But now we have to do something more to that. Okay. So if that is the case, we are interested in actually finding the extremum. We would like to set this to 0. That's equal to 0. That means that And that's a condition for the geodesic, right? So this is a condition for geodesic. If it's a geodesic, the shortest path, then that's equal to 0, right? So from this point on, now we are going to physics. Right? As of now, it is mathematics, the functional derivative, but now we're getting into the physics to see what does this mean, what can we use this for. And we have found the derivative. So we say this is dy prime. So let's say for the time being y prime. Y prime means dy by dx. Temporarily, I won't use it too often, but it's convenient to use it here. 1 plus y prime squared. That's equal to 0. Derivative of something is 0. That means that quantity must be constant, right, with respect to that parameter of derivative. So I can immediately say that y prime over 1 plus y prime squared has to be a constant. We don't know what the constant is. Usually that's an integration parameter, but using initial conditions, we can know what that is. How can we find that C right away at this point? Right? We can remember that this is all y prime, but this is with respect to x, right? So notice this is a y prime of x. Like y prime means derivative, right? With respect to x divided by 1 plus y prime of x squared, so the derivative of x squared, that's equal to C. So it seems like I can find C. Remember your point here was x1, y1 and x2, y2. And we're talking about which path actually is equal to 0, but somehow the C has the information of this tangent here. So x, so whatever the path is, you take the derivative. If you know the derivative at x equal to x1, right, that ratio is a constant. But then, if you realize that what this seems to suggest is that it's not, this derivative doesn't have to be at x1, right? I can take the derivative at any point. Any point you take the derivative, if I know the derivative divided by that derivative, apparently that's a constant. But that's true for every point, which seems to suggest that this itself must be a constant. How is it possible that the ratio of the derivative divided by 1 plus the derivative square is a constant? How is that possible? It seems to suggest that the derivative itself is a constant. But let's see how that comes about. Okay, let's not presume that algebraically we should be able to see that, right? So let's square that. So let's start from here and let's square it. So this point is saying that y prime square. When I square this, this is c square times 1 plus y prime square. Remember again, that's derivative, right? Y prime is derivative. Bring it to the left hand side. So that's 1 minus c square. C is a constant. Prime square is equal to c square. That means y prime is equal to c over 1 minus c square, which is right. So what we have is dy by dx derivative of y with respect to x is a constant because c is a constant divided by 1 minus c square is also a constant. This is a new constant if you want. So this is c bar, or let's say c1. C1. Right. Because c is a constant, that's a new constant. And that makes it very clear, right? Oh, the slope of this special path, this is now no more an arbitrary function. This is the equation of a geodesic, right, on a plane. So what is the equation of the geodesic? Just integrate this down, that should be straightforward. So this implies that y of x is equal to c1 of x, but when I integrate this, I get a new constant, right? So that's c2. But is c1 and c2 arbitrary? No, because we have some conditions here, right? At x1, it has to satisfy y1, right? So what is c1 and c2? We have two equations here, and those are at x equal to x1, y is equal to y1. So that means y1 is equal to c1 x1 plus c2, and at x equal to x2, y is equal to y2. So y2 is equal to c1 x2 plus c2. So clearly c1 is the slope, so c1 will be, you can add these two quantities, right? If I subtract, actually c2 goes away. So if I subtract them out, so then I get c1 is equal to y2 minus y1 divided by x2 minus x1. I get y1 minus y2 divided by x1 minus x2, but I change the sign. So c1 is determined by the initial conditions in terms of y2 minus y1. And what is c2? Once I know this, I want to cancel that out, right? I substitute c1 and get c2, I suppose, right? So c2 would be equal to, let's say, y1 minus of x1 times c1. c1 is y2 minus y1 divided by x2 minus x1, which is equal to y1 x2 y1 x1 plus y1. So y1 x1 cancels out, so it is y1 x2 minus of x1 y2 divided by x2 minus x1. So you know c2 also. So our equation is, for the specific 2 points, is equal to y of x is equal to y2 minus y1 divided by x2 minus x1, just writing it explicitly, x plus c2 okay. So that completes that problem. Typically, when we say geodesics, geodesics are parameters of C1 and C2, so we want to keep this independent for any 2 points. Then C1 and C2 is described in terms of those 2 points. Does that help? Like I went through in detail, but hopefully that helps. We'll come back and do this for a sphere. At that time, there will be more non-trivialities in the sense that we'll be working in spherical coordinates. But for now, let's actually build on a problem that we started in about a week ago. That's how we motivated the whole functional derivative. We talked about optical problem, right? there is a refractive index, how does light go around. And now let's make that more specific, and that's what your homework is about. I will do one particular situation here, and in the homework you have to do that for another configuration if you want another geometry in a sense, if the refractive index is given you. Yeah, before that, any comments or anything that is not comforting here, because everything should be crystal clear so that we can proceed forward. Yeah. Yes.
I see how the y2 minus y1 divided by x2 minus x1. I see how that's the slope. How is the other one like the y-intercept though? Like, so when you make the
How is it? Okay. You would like to see the physical interpretation there. That's the point, right?
if it's quite trivial.
I actually don't know. Let's see. C2 should be the y-intercept. Yes. Let's see if, yeah, so can we take some limits and see? So what we're saying is that we have two arbitrary points here. So this is x1, y1, and x2, y2. And that's your point, right? So what is the C? That's how you would find out, right? What's the C? So you would say that's your C here, correct? That's your y2, that's your y1, and that's your C. Okay. X2 minus x1, so that's this. X2 minus x1, and y1 times x2. Is there any obvious way of seeing this? So what is this distance? If I know the slope here, right? Right? That's my slope. What is this distance? Right? That's your x-intercept, right? So x-intercept is when y is equal to 0, correct? Which is x. So this is equal to minus C1, C2 over C1. Right? But probably I'll be going in cycles there, right? Oh, sorry, this is C2. So this square or tangent of this is this divided by. But I'm already having C2 in this. Probably I don't want to use that. I want to use this geometry. How? It should be possible. Okay, again, y1, x2. So this seems like a cross product, right? So this cross product seems to suggest that this is the area of the triangle. So y1, x2. y1 times x2. Don't have much idea of this, but trying a little. Let's see. Yeah, this is your x1, y1, you're saying, and x2, y2 is here. So the area of this parallelogram apparently is your y1 x2 minus x y2. C2. Okay. Again, I think this should be straightforward. Let's again see C2 here. That's your y1. That's your x1. That's your y2. And that's your x2 minus x1. Y1 times x2. I don't know. Chris. Anything I cannot do, you should do. Yeah, but this should be doable, right? This is coordinate geometry. Yeah. Why do we have this? Because this is nothing to do with what we are doing here, right? Like if we have an equation of the line, if we know 2 points, then the y-intercept is given in terms of those 2 points like this. And yeah, let's look at this more carefully. Maybe go back and look at it like this. So x2 minus so y1 times x2 minus x1 because there's a cancellation there, right? Minus of x1 times y2 minus y1 divided by x2 minus x1. So that's how this looks like. There's a slope here. Slope multiplied by x1. So the slope multiplies or tangent theta multiplied by x1 is this y1. That's y1. So that's y1. And this one is y1 minus y1. I don't know. So it shouldn't be 0. y1. Oh yeah, so here's how you can see this, right? Yeah. So this piece, so this is just y1, right? So the first piece is y1 minus of, I mean, I'm probably going in circles, so this is slope, right? X1 times
go back here, y1 minus x1 times the slope. Right? So here it is clear, x1 times slope is nothing but so x1 times the slope. Like what is that equal to? So if you go x1, that will give you y1, right? So this is nothing but y1, but that is y1 is actually C2 plus how much ever you go from there. See what I'm trying to say? So maybe, okay, again. So we have, this is your C2. This is your 0. And somewhere here is x1. If I go x1 horizontally, how far do you go? That's decided by the slope. This quantity is actually x1 times slope. That's the definition of slope, like what is this called? Run versus rise, right?
Rise over run.
Rise over run, right? So this is run times the slope should give you the rise. Right? So that's your rise. Right? And y1 is the whole distance here. Okay. So y1 minus x1 times slope is actually C2. At least in this form it is clear, but now why is this true? So that was your original question. I am not answering that, but at least I can see this. Right? So it's basically this point. This is sort of there is a parallelogram here, right? So if you were to think of x1, y1 here, that's one point, and that x2, y2 as another point, I can actually derive parallelogram. And the area of this parallelogram is given by the cross product. Somehow that C2 is related to that. I'm not seeing that. Okay, that's interesting. I can know. C2 times x2 minus x1, right? What is C2 times x? C2 over, or C2 times x2 minus x1. So x2 minus x1 is here times C2. C2 is there. That here. I don't know. Good point. Yeah. So there is some geometry playing a role here. It is nice to see why is that area showing up, area of that parallelogram. It's kind of, I think, neat there, and which must have been written down somewhere. Yeah.
Thank you.
Yeah. So let's keep that as a quiz. Why is that area showing up? Again, remember, quiz. You don't have to spend too much time, but they're good exploratory question. So why is that area? So what's the meaning of the numerator of C2? So it's just good question. I don't know the answer to that. Okay, having said that, I'll let the last 10 or 13 minutes, let me at least construct another problem, which we talked in terms of stratified medium. Now let's make this better. Okay. So this is what's called Fermat's principle. Fermat's principle in optics. And we sort of touched on it, but for stratified medium, what we said was that if we have N1 here, let's say this was, let's say this is N1, that's N2, and that's N3, and so on.
we said if light comes from here, and assuming that N1, N2 is greater than N1, this will bend, right? This will bend down here. So let's say this is N2 is greater than N1, N3 is greater than N2. Then it will bend here a little more, and this will keep going like that, right? And at each point, Snell's law is obeyed. Correct. But we can generalize this. Let's say that we have a continuous distribution of refractive index, which is a function of x. So n increases to the right. To specify that clearly, because remember, refractive index has to be greater than 1, right? N was equal to c over the speed of light in the medium, which is always greater than 1. Greater than or equal to 1, let's say. If you're in vacuum, n is exactly equal to 1, otherwise it's so let's specify the system to be the following. If so, there is a special point A less than that. If you are less than a certain point A, you have vacuum onto the left. And once you cross that vacuum, refractive index keeps increasing x over A. So this is, so let me draw that better. So if I were to plot this, so this is your x dependence here. Somewhere there is a point A. I don't want to say that that's actually the origin, because if it is the origin, then the way I have defined it, it will diverge, right? So it is somewhere to the right side of the origin. Right? So let's say this is somewhere here is 0. Right? So that sets the scale for the problem. And if I were to have that to be measuring your refractive index and as a function of x, until I reach the point A, the refractive index is exactly 1, right? That means it is vacuum everywhere here. And it doesn't have to start from origin. It can be everywhere here. So it's vacuum here. And at this point, now there is a medium. Right? It's like, think of this as an atmosphere. Like you have the Earth's atmosphere beginning here, right? Slowly it starts getting denser and denser. Right? But as you go from this point onwards, it actually linearly increases, and it keeps rising. So by the time you get extends to infinity, refractive index is infinity. So that's a very special choice you have. In your homework, it is exactly the opposite. I say between the origin and 0, it is 1 over x. So it is 1 over x for x less than 1. So it is very dense at the origin, and then it gets rarefied as you go farther and farther. So that's your home. So it's an opposite, but the systematics of the functional derivatives remains the same. Okay, so that's your enough. X is given to us, and let's say you start from some point x1, y1, and you go to another point x2, y2. So for a small distance that you go, dt is equal to, remember there is y also, right? So this is x, and I have plotted this with n of x, but in general we have median, right? So this is stratified median. So this is your y-axis now, and refractive index increases in this direction. Is it clear? So notice this is x with respect to n of x, and here this is the actual space, x and y. Light comes here, and as it goes, the medium gets denser and denser. This is not that.
this is actually showing that refractive index as a plot with respect to x. So this is a stratified medium. Is that clear? So this is very light, right? At x equal to a, and then it gets denser, denser, denser. Is that clear? So refractive index increases as you go to the right, but it is stratified nevertheless. Like these are layers. Is that clear what I mean by that?
When you say stratified, that's, you're saying it's like a density?
Yes, density. So density is less here. Stratified means there is a symmetry, there is a planar symmetry. Like in the YZ direction, there is nothing happening. So the density is the same except in the X direction where it increases. Right? So there is a YZ symmetry. So in that sense, dt now is equal to how much ever I travel, because I can travel from here to there, right? Notice if so why I say that point is that when I travel in that direction, there is a little bit in the X direction, but Y direction, I don't lose anything. So information content is in the all the speed issue is in the X direction, right? Which is the correct one. So I would like to go more in the Y direction and less in the X direction, because that side is more denser, I'll be slower. Right? If, for example, if I had to go from here to there, I don't want to take this path. Right? Probably I want to take this path. Right? So very less here, and then, but that might be too much pricey. So somewhere here might be more economical. So something like that. So it's the path that comes in, and that immediately tells me that it is ds divided by the speed. Right? So that's the time for any small variable is ds over velocity. Right? That's your definition of velocity if you want. And that's the same as v is n over c. Right? So n over c times ds. So if I have to go from one point to the other, the total time t will be equal to dt going from x1, y1, point x1, y1 in this plane if you want, to x2, y2. In general, this is a three-dimensional quantity, but let's say this is happening in a plane, so that just to avoid one parameter variation. So that's the same as if I write this everything in terms of x1. So this is x1 to x2. dt is this quantity, so this is n of x over c. ds is nothing but dx times square root of 1 plus. Is that clear? And again, I used ds as so our functional would be t as a function of the path y. We don't know which path this light will take. Let's keep it arbitrary. And that's equal to 1 over c if we want. So that c is the constant speed of light. x1 to x2 dx. Refractive index n of x times 1 plus dy by dx squared. Very similar to what we had earlier, except that there is a refractive index showing up in between. so what does format say? Format's principle is in the language of functional derivative is that for the particular path that light takes, for the very special path, this is actually equal to 0. It's an extreme. So if we can find that solution, that will be your, and that's what we will do next time. So this sort of constructs the problem. And once we do this, we'll slightly change the refractive index distribution, and that's your homework problem. So on Thursday, we'll work on this, and that should give you help with the homework. Yes, Christian.
What is the large D again?
Large D.
T, sorry.
Oh, large T is the total time it takes to go from here to here. Right? And I want to minimize that. So light doesn't take the shortest distance. Earlier when geodesic is a path of shortest distance. Here we're talking about shortest time. And there is a word for this, later I will call this a brachistochrone. Right? The shortest time will be called a brachistochrone. I mean, you can look it up also. There is this brachistochrone is a special path. It's in the context of gravity, but in general, we will call it the brachistochrone, means whenever the time is minimum. That's how we will define it here. Yes.
And next question.
Mhm.
You chose to make it a functional of y because of the density, correct? Like if it was, let's say, in the other direction,
Yes.
you would then want it to be a function of x.
Functional of x.
For that.
In fact, at this point, she says, since there is symmetry, right? So who says that it should be x? So for example, I can say that there is x1, y1 to x2, y2, right? That is all the information that's there, right? And that's x, sorry, this is x, and that's y. Correct? And now, what I have chosen to do is think of this as a function of x. Why someone else could come and say that, oh, why should I think of this as a function of x? I will rotate myself, I will bend down, right? And think of this as x as a function of y. Why not? Then you're thinking this is your independent coordinate and that's your dependent coordinate. That's perfectly fine. There is a corresponding thing here. This is also equal to y1 to y2 dy. Then you will take dy common out there, dy, and then n of x. And we have 1 plus dx by dy the whole square. But having said that, this is tricky because now you're going to be varying x here, right? So since refractive index is a function of x that is given to us, it is convenient to do this, a lot more convenient to do this. But as far as concept goes, this should be exactly the same as this. In fact, often there are problems where by construction you will be actually doing this, but then it is very hard to do this. So you will use this analogy and you'll jump into that, and it will be easier to do. Right? So we should be able, and that's called the Beltrami identity. That is an identity which allows you to switch from one to the other. But because as far as the problem goes, there is complete symmetry in there. Who says I cannot vary that? Good question. Yeah. Okay. Okay, let's stop here.